Hi everyone, this is Anushka and welcome back to my channel AN Economist. So if you are someone who is following my lecture videos on panel data, you will know in the previous few classes we have discussed the concept of panel data, and then we have gone into the different estimation methods of panel data, right? So we have discussed what is fixed effect model, what is random effect model, what is pool OLS method of estimating the panel data, and also other methods of different degrees of flexibility. We have already covered this portion. If you are new to my channel, welcome, and please watch those videos before going into this video, because this is going to be the final part, the only portion that is been left in our discussion of panel data, where we will discuss firstly what is the difference between the fixed effect and the random effect model. So we will go into the detailed distinction between these two methods, or these two estimation process of panel data. And then we will also discuss a statistical test which is known as the Hausman test, which basically helps us to understand, which helps us to determine which method to use in which scenario, right? So we'll conduct statistical tests, we will form hypothesis, and we will mathematically test that which of these following methods you have to use in which scenario, and how the test, the Hausman test, dictates you to do so, right? So this is the agenda for this video. Now let's jump into the topic. So firstly, understand what is the difference between the fixed effect and the random effect model. So I have made detailed, discussion videos on these two topics individually. If you have not seen those videos, I'll give the link in the description. Also, you will find that in the I tab button. Please check that out before going into this video. So here I have given you a summary table, as you can see here, where you will get more clarity of what we have done. So this is basically a summary chart. So see, the first point of difference, which is the most crucial difference, this is the main distinguisher between the fixed effect and the random effect model, which says that in case of fixed effect model, individual effects are correlated with the regressor. So individual effect means the unobserved heterogeneity. Remember, we have studied this, the unobserved heterogeneity. Suppose you call that AI, unobserved time invariant heterogeneity, this thing which is usually considered to be unobserved. In fixed effect model, what we assume, this unobserved heterogeneity becomes correlated with the explanatory variables, or the regressors of your model. This is the case of fixed effect. See, this is the unobserved heterogeneity AI, and this is the observed explanatory variables in your model. So the basic assumption of fixed effect model is that the individual effects, this time invariant individual heterogeneity, this effects will get correlated with the explanatory variables or the regressors of your model. If this is the case, then you will say the model is fixed effect model. And in case of random effect model, exactly the opposite is true. This unobserved effects will be uncorrelated. This will be exactly equals to zero. So this is exactly uncorrelated with the regressor. So this will also form the base of our Hausman test. This we will see. While forming the hypothesis in our Hausman test also, we will use the same condition. So understanding this first point is very important in order to go into the Hausman test. That is why I have given you this detailed summary table. I know many students find it very difficult to understand, but this is the main point of difference that we need to know, right? So this portion is done, that in case of fixed effect model, the unobserved heterogeneity or the individual effect will be correlated with the regressor. That is, this covariance will be not equals to zero. But in case of random effect model, this covariance will be just exactly equals to zero, which means that will be uncorrelated with the regressor. Now look at the second point, which reflect the estimation process. This also we have discussed in detail in our previous videos. Here I have written the summary of it, that in case of fixed effect estimation, what we do the within transformation, or we use the time domain data on y, x, and also on the idiosyncratic error term. So basically what we do in order to estimate the fixed effect model, we use a transformation to firstly remove the unobserved effect. Right. So if this unobserved heterogeneity is present in our model, then we cannot estimate the model, right? We have discussed this previously. So what you have to do, you have to introduce the time domained data on y, x, and also on the idiosyncratic term. And how do you do that? You firstly take the summation over all t, right? You take the mean, you take the average over the time period, across the time period, in order to eliminate the the unobserved effect, in time invariant effect. And then what you do, then you get a model, you land up to a transformed model, which is also known as the fixed effect transformation or within transformation, right? The transformed model that we land up to after removing this unobserved heterogeneity is known as the fixed effect transformation or the within transformation. And once you get this transformed model, then it becomes eligible for pooled OLS estimation. So on the transformed model that you get from this method, we apply the pooled OLS regression on that to derive the estimates of the coefficients, right? So that is the general process. This we have also discussed mathematically. We have derived everything. So I would again recommend you to see that video if you haven't already. Right. So again, I am repeating this thing that in case of fixed effect model, in order to estimate, firstly, you have to remove the unobserved effect, namely in terms of AI or alpha I, whatever you call it. So this unobserved effect has to be removed firstly. This cannot be present in your model. Either you can use the dummy variable. This is another method that we have discussed, least square dummy variable, or more preferably, you use the demean, time demean data. You do the within transformation and you land up to the within effect model or transformed model on which you apply the pooled OLS method in order to get the final estimation. So that is what we do in the fixed effect model. Now, what about the random effect model? In random effect model, firstly, what we do, we generate a composite error term. This is the, last video that we have done, random effect model. There I have discussed this, that in case of estimating the random effect model, we generate a composite error term, which contains this unobserved heterogeneity, right? Which contains this unobserved heterogeneity. And then what we do, we apply the generalized least square. Random effect model is estimated using generalized least square. We apply the GLS method in order to estimate the parameters of this model. So if you remember, we have taken into account a parameter, a constant basically, which lies between 0 and 1. And using this fixed value, using this parameter, we have transformed our model. We have got our transformed model, and on that, if you apply the generalized least square, then that will give you consistent estimates under the random effect. So again, in case of random effect, what we do, we firstly generate the composite error term, which contains this unobserved heterogeneity, and then we transform this model on the basis of an appropriate fraction that we define. Right? Basis of the features of the model, we define an appropriate fraction, which helps us to get the transformed random effect model. And then on that transformed model, you apply the generalized least square method, which helps you to find out consistent estimates, right? So these are the basic two difference between the fixed effect and the random effect model. Now, if you understand this, the rest of the things becomes very easy. So the third point says time invariant variable. We know in case of fixed effect model, it is excluded. So we cannot work with this time invariant factor. So we simply exclude it. But in case of random effect model, this time invariant factor is included. It will help us to estimate the model. So it is included. Number 4 is efficiency. We generally assume that random effect model is more efficient, right? Fixed effect model is less efficient if the random effect estimate assumptions hold. So basically, we have done different assumptions of random effect model. If those assumptions hold, then we should blindly follow the random effect model because that is a more efficient model, which is a more efficient model. So random effect model is more efficient if random effect assumptions hold. Otherwise, we should use the fixed effect model. Consistency, fixed effect model is always consistent, but random effect model can become inconsistent if the assumptions are valid. And then we have the Hausman test preference. This we will do next. This is the agenda for the next segment of this video. So I'm not going into this. We will see how we can define the null hypothesis and alternative hypothesis. Then you have degrees of freedom. So remember that in case of fixed effect model, we introduce dummy variables, right? In order to eliminate this unobserved heterogeneity, we introduce different dummy variables in our model. And as soon as you introduce new variables in your model, the degrees of freedom will definitely be lower, right? Due to individual heterogeneity. So we know that degrees of freedom is what? Total number of variables minus the number of parameters that you are introducing in your model. This will give you the degrees of freedom. Now, as soon as you keep on introducing new dummy variables, the number of parameters will increase. So altogether, your degrees of freedom will come down, right? So in case of degrees of freedom, fixed effect model is not good. The degrees of freedom will be lower. But in case of random effect model, since we do not need any dummy variable, the degrees of freedom will be higher in this model, right? Now, next up, we have the interpretation. See here, fixed effect model controls for all the time invariant heterogeneity, right? So we again, this everything comes from this point that we cannot have this AI term into our model if we are working with the fixed effect. So that is why it controls. Fixed effect model controls for all the time invariant heterogeneity. Whereas in case of random effect model, it assumes heterogeneity is random and it is uncorrelated. So we have in details discussed what are the different assumptions of random effect model. There we have assumed this, that it assumes heterogeneity is random and also they are uncorrelated. This is just the what we have discussed in the previous video basically. And now the important point, when should you use this? That will be determined by the Hausman test. But in general, when the omitted variable bias is a concern, then we should always use the fixed effect model, right? Omitted variable bias, this also we have discussed in our specification error chapter. This is present in our advanced econometrics playlist. So again, if you haven't watched that video as well, I'll give the link. Please check that out. What is omitted variable bias? I have a separate lecture video on this. So when we are concerned about omitted variable bias, then we should use the fixed effect model. Whereas when the unobserved effects are believed to be random, when randomness is inherent in the model, we should blindly follow the random effect model. But in general, mathematically, if you want to test this thing, we need to go into the Hausman test, and that is what we will do now. So this is a very important statistical test, Hausman test, as you can see. So Hausman test is a statistical test used in panel data analysis to decide whether to use the fixed effect model or to use the random effect model. As you can see, this test was developed by Professor Jerry A. Hausman. So I have taken this picture from Investopedia, so all credit goes to them. So this is the professor. He was the professor. He was the director of MIT Telecommunications Economics Research Program. He was professor of economics and applied econometrician at Massachusetts Institute of Technology, MIT. And all the credits for developing this Hausman test goes to him, right? So Professor Jerry A. Hausman developed this test, and hence the name of this test is Hausman test, right? So now next up, we will see what is the intuition of this test. So this intuition is coming from the difference between the fixed effect and the random effect model, what we discussed in the previous slide, right? So see here, in case of fixed effect model, this we have seen, it assumes that individual specific effects. So this individual heterogeneity can come from the firm level or it can be the country level heterogeneity, anything. They are correlated with the regressors. This we have seen earlier that AI XIT, if it is a fixed effect model, it will be not equals to 0. So this is where the correlation comes into the picture. So unobserved individual specific heterogeneity will be correlated with the regressor. But in case of random effect model, this will be uncorrelated. So this statistical test has been formed. So see here, what do we do in case of Hausman test? Hausman test checks if the assumption of no autocorrelation is the assumption for the random effect model. If the assumption of no autocorrelation holds or not. If it holds, then we will say that yes, random effect model is better than the fixed effect model. But if it does not hold, then random effect estimator becomes inconsistent and we go into the fixed effect estimation. So this is the simple trick that we use to estimate this model. So what is the intuition? If we see, so the null hypothesis will test basically the covariance of AI XIT is 0 or not. If we see that this is true, then what we do? We say that yes, no correlation exists, which means we should blindly follow the random effect model because the random effect assumption is being holding. But if we see that this does not hold, if this assumption violates, then we will say the random effect estimator is inconsistent and we should follow the fixed effect model, right? So this is on the theoretical level, this is the intuition. Now let us formally define the null hypothesis and the alternative hypothesis, which we have done here. So see, null hypothesis, which is denoted as H naught. Here we will assume, our assumption is that random effect model is consistent and efficient, which means that we prefer random effect model. So null hypothesis assumes that covariance of AI XIT is basically zero. This is our null hypothesis. And in alternative hypothesis, we assume just the opposite, that the random effect model is inconsistent due to the correlation. So in random effect, we assume that this correlation exists. This correlation exists, which means that covariance is not equals to zero, which means that we prefer the fixed effect model. So remember that in case of Hausman test, the H naught assumes that random effect model is preferred, and the alternative hypothesis assumes that the fixed effect model is preferred. Right? Now, how do you decide on the rule? Let me show you. To land up to the decision rule, we need to have a test statistic. In any hypothesis testing, we know we should formulate a test statistic. Now, in case of Hausman test, this is the test statistic that we use. So see here, Hausman test statistic is denoted by H, where what you do, this is first term is beta cap RE. So this is the estimation. So this is the estimation that we do under the random effect model, minus the coefficient estimation under the fixed effect model, and a transpose of that. So this thing is basically the transpose. This basically implies the transpose. And then what you have, variance of beta cap fixed effect minus variance of beta cap random effect, and the inverse of that multiplied by this. So this is written in the matrix format basically, because we do not know how many regressors are there in the model. If you take the simplified case, if you take only one regressor, then the statistic will boil down to this. So beta cap RE minus beta cap fixed effect, and this will be a whole square, because see here you have transpose and here you have another thing. So they will get multiplied, it will be whole square, and this inverse will come here. Beta cap fixed effect minus variance of beta cap random effect. And this statistic under H naught will follow chi-square distribution. Under H naught, let me write it down. Under H naught, this test statistic will follow chi-square distribution with say V degrees of freedom, where this V is nothing but the number of the regressors which are present in our model. Right? This V will be, if you have only one regressor, it will be one. If you have two regressors, it will be two, and so on and so forth. And then you will, specify a level of significance, and then we will conduct this particular test. The larger the value of the test statistic, we will reject the H naught. So we know is that this is the chi-square distribution. This is how the chi-square looks. It starts from the zero. It's a right tail test. So the more, suppose this is the critical value. So if the chi-square statistic is very large, and suppose you go into this particular direction, it means you will reject your null hypothesis. Right? Reject your null hypothesis means rejecting the possibility of applying the random effect model, and here we are saying that we will use the fixed effect model. And if you are in this particular zone, then your null hypothesis is accepted, which means you will use the random effect model itself, right? So this is how you decide on the rule. Now to get things more clear, I have given you a numerical example. So here let us see how we can apply this Hausman test for our purposes. So it's basically a hands-on exercise where we will see numerically how to perform this. So see here, this is the numerical example. Let's say we have the following simple panel regression. So see, I have taken a hypothetical regression for you. This is just to make you understand the concept, nothing else. Right? So YIT, as you can see, YIT is the outcome variable. Beta 1 is the only coefficient term here. Beta 1 is the only coefficient, and you have only one regressor. Right? Only one regressor is there. XIT is the only regressor. UI represents the unobserved individual effect, basically unobserved heterogeneity. And epsilon IT is the idiosyncratic error term that we always assume in case of our panel data. So here you can see this is the dependent variable, this is the regressor, and this is the unobserved individual effect. Now for this particular model, suppose what you do, you estimate this model. Suppose you estimate this model using both random effect and the fixed effect. Right? You estimate this model using both random effect and fixed effect. Using random effect, you have found out what will be this beta 1 cap, right? You have estimated this, so you will find out the estimated value of this. Also, you will find out the variance of using this random effect model. You will do the same thing using the fixed effect model, beta 1 cap and variance of beta 1 cap. This you will find using the fixed effect model too, right? So you will firstly estimate this model using both random effect and fixed effect. After the estimation, suppose this is the result that you will get. Again, this is a hypothetical scenario. This is just to make you understand the things, right? You can generate your synthetic data set in Python, in R, in Stata, in whichever platform you want. I have generated a synthetic data set and then I have used this. I'll show you in my, Python videos how you can do this in Python and all the other softwares. We'll make a separate playlist on that. As of now, I have just pasted the output that I have got. So in case of fixed effect, see, in case of fixed effect, this is the beta 1 cap. This is the beta 1 cap value that I have got 2.5. And this is the variance of beta 1 cap, which I have got in case of fixed effect. Similarly, for random effect, these are the data points that I have got. So if you have this information, then what you have to do, check which model is better using Hausman test. So see, if you have this particular information, can you compute the test statistic? Can you pause the video and think? Can you compute the test statistic? The answer is absolutely yes. So see, this is the Hausman test statistic. So you have beta cap random effect, you have beta cap fixed effect, you have variances also. Under each knot, it will again follow chi-square with only 1 degree of freedom because you have only one regressor here. See, in this model, you have only one regressor XIT, so you can definitely do that. So let us now compute this. Let me show you how you can compute this. Computed Hausman statistic is given by, so this will be H computed. H computed, it will be simply given by, firstly we will write beta cap. Let me go back. Firstly, you will write beta cap under the random effect. So beta cap under random effect minus beta cap under fixed effect whole square upon variance of, firstly you will have the fixed effect and then you will have the random effect. Fixed effect and then you have variance of the beta cap random effect. So all the data points are available to you. So what is beta cap under random effect? From this model, if you see, beta cap under random effect is 1.8 and beta cap under fixed effects is 2.5 whole square upon the variances. So the variances will be 0.04 and here it will be 0.02. Right now, if you compute, I have already done this. This will be 0.49. This will be 0.02. If you do this calculation, this will come out to be 24.5. So 24.5 will be the computed H statistic. It is the computed value. And what is the critical value? The critical value will be chi-square. Suppose I take 0.05 is the level of significance and there will be only 1 degrees of freedom. Here at 5% level of significance, the critical value is 3.48. So what can you say? Let me draw a rough diagram. This is a rough diagram. I'm just showing you to and make you understand what is happening. So the critical value is this 3.84. This is the critical value that you are getting for. But the computed value is way more. 24.5 is somewhere here, right? Way more in more in the rejection region. This is in the rejection region. So what we can say here is that 24.5, or let me write H computed is greater than H critical basically. So what we should do? We should reject the null hypothesis. It definitely means we should reject the null hypothesis, and rejecting null hypothesis means fixed effect model should be preferred, right? So this is how you conduct the Hausman test. I hope I have given you a simplified, explanation of how to conduct this test. Definitely, manually, it's not that easy. Here, I have taken a oversimplified example. In panel data. You hardly have this kind of a simplified model. You usually do this in case of, in using Python and R and Stata. That I will do in a separate video. But just to give you an overview, a simplified explanation of how things work in the panel data scenario, I have given you this thing. So remember that in the Hausman test, in the null hypothesis, what we assume? Null hypothesis, we assume that random effect model should be preferred. But here in our numerical example, we have seen we should reject H naught. We should reject H naught means alternative hypothesis should be chosen. That is fixed effect model will be better in our particular scenario, right? So this is how you numerically do it. So the summary table is given to you. So in Hausman test, what we do? The condition is Hausman test fails to reject H naught. If we have failed to reject H naught, which basically means we accept H naught, then random effect model will be preferred. And if Hausman test rejects H naught, which basically means that alternative is been accepted, which means we need to use the fixed effect model, which is the scenario what we have got in our numerical exam, right? So this is all about the content that I wanted to share with you about panel data. I hope you liked this video, and with this we have ended our discussion on panel data. If you have any questions from any of the lecture videos that I have posted so far, you can please let me know. I'll be more than happy to answer your queries. And if you like this video, if this lecture videos are helping you to understand things better, to update your marks, and it's adding value in your life, so please hit the like button and do hit the subscribe button also. Do subscribe to this channel in Economist, because that helps me immensely. That motivates me to make such useful videos for you in every single week. And I try to make 2 to 3 lecture videos. I post 2 to 3 lecture videos every single week, and which takes a lot of effort from my end. So if you feel that these videos are useful, then please support my endeavor, show your love and support towards this channel. And I'll meet you in the next video with some new topic, right? So thank you so much for your time, and let's see you in some other video. Thank you.